All right, welcome. If you've ever had to design a database from scratch, you've definitely hit this wall. It's this fundamental choice you have to make right at the very beginning, a classic dilemma that pits this idea of a perfect, organized system against raw, unadulterated speed. Let's dive into it. So, what's the big question we're wrestling with here? It's this. Are you going to build a database that's a model of pristine organization, where every single piece of information has one and only one home? Or do you build for lightning fast performance, even if it means you have to repeat yourself and copy data all over the place? That, right there, is the great trade-off. Okay, so let's start with the path of the purist, right? The by-the-book approach. In the world of databases, this quest for perfect order has a name: normalization. It is all about creating a database schema that's clean, logical, and has absolutely no repetition. So what exactly is normalization? Well, the official definition is right there on the screen, but let's just break that down. In the simplest possible terms, it's about following one simple rule. Don't repeat yourself. Store every unique piece of information in exactly one place. Period. And why do we bother with this? What's the point? Well, when you get rid of redundant data, you get something incredibly valuable in return: data integrity. It means you can trust your data. This helps prevent all these weird bugs, or anomalies as they're called, where you might update a piece of information in one place but forget about it in another, leaving old, incorrect data just lurking in your system. To really make this click, let's look at a super common example. Imagine you're building a system for a library, and you start by just dumping everything you know into one giant, kind of messy spreadsheet. Okay, look at this. You can see the problem right away, can't you? For every single book Herman Melville wrote, we're also storing that he's American. If he wrote 20 books, we'd have American listed 20 times. That is the definition of redundancy. Now, imagine you need to update his nationality. You'd have to hunt down every single entry and change it. If you miss just one, bam, your data is now inconsistent. You're just asking for bugs down the road. So how does normalization come in and save the day? Well, it cleans up this mess by doing something really smart. It splits this one big table into multiple smaller, much more focused tables that are all linked together. First up, we create a table that only cares about one thing: the books. Take a look. No more author name, no more nationality. Instead, we have a simple reference, a pointer, called author ID. This table's job is to know about books, and that's it. So, where does that ID point? It points right here to our shiny new authors table. Now, Herman Melville's nationality is stored in exactly one place. If we ever need to change it, we change it here, just once, and every single book linked to author ID 101 is automatically updated. It's clean, it's efficient, and it guarantees our data is correct. Now, for those of you who want to go a little deeper, especially senior engineers, you should know this process isn't random. It's formalized into levels called normal forms. You have first, second, and third normal form, and each one adds stricter rules. We're not going to get lost in the weeds here, but just know that reaching third normal form, or 3NF, is a really common goal for a well-structured database. Okay, so normalization sounds pretty perfect, doesn't it? Clean data, no redundancy, everything is safe and sound. What's the catch? Come on, in software engineering, there is always a catch. And there is indeed a price to pay for all this data purity. So here's the downside. Because our data is now split up, if we want to get a full picture, like a book's title and the author's nationality, we have to do this little dance. We have to go to the books table, find the author ID, then jump over to the authors table to get the rest of the info. In database language, that jump is called a join. And when you have lots of tables, making the database do all those joins over and over, well, it can get slow, really slow. So, if the correct way can be slow, what's the alternative? This is where we, as engineers, start to bend the rules. And we do it for a very good reason: raw speed. So let's talk about the other side of this coin: denormalization. Denormalization is exactly what it sounds like. We are intentionally adding that redundant data back into our database. I know it feels a little wrong after everything we just said, but we're doing it strategically. We're looking at slow parts of our app and deciding to trade a little bit of that data purity to avoid those expensive join operations and make our queries run faster. But of course, breaking the rules always has consequences. When you choose to denormalize, you have to be very aware of the trade-off you're making. You're giving up that automatic data integrity that normalization gave you, and you're doing it for one thing and one thing only: performance.
So let's just lay it all out. On the pro side, your data retrieval can be way faster. And honestly, your queries can be simpler to write because you don't need all those joins. But the cons can really bite you. You're wasting storage space, sure, but the really big one is that risk of data inconsistency comes roaring back. If that author's nationality changes, it's now your application's job to remember every single place you copied it and update all of them perfectly.
So now we have these two completely opposite philosophies, right? Normalize for integrity or denormalize for speed. How in the world do you choose the right strategy for your project?
Well, it almost always comes down to your application's workload. Is it doing a lot of writing or a lot of reading? Systems with tons of writes, think an e-commerce site processing orders or a banking app, those are called OLTP systems. For them, data integrity is king, so you absolutely normalize. On the flip side, systems designed for analysis with a massive volume of reads, like a data warehouse for business reports, those are called OLAP systems. Their query speed is all that matters, so you denormalize like crazy.
But here's the real-world secret. It's rarely all or nothing. Most modern systems end up using a hybrid approach. The common wisdom, what a senior engineer will tell you, is this. Start with a perfectly normalized design. Keep it clean and safe. Then you monitor your application, and only when you find a specific performance bottleneck do you go in and selectively denormalize just that one part of the system to speed it up. You get the best of both worlds.
So I'll leave you with this question to think about. The next time you're working on a feature and it's running slow and you trace it back to the database, what's your first instinct going to be? Are you going to break the rules and denormalize for that instant speed boost? Or are you going to stick to data purity and try to find a more clever way to optimize your queries? The answer really defines your philosophy as a developer. Thanks for watching.